Hello, I'm Quinn Phelps, the Project Manager for Student Engineering Services, and today we will be presenting our design for the Shaw Power Plant project. We will start off with the location of this project. The existing Shaw Power Plant is represented by the star on this map of Michigan State University. As you can see, it is located relatively central to campus near Spartan Stadium. The existing building was constructed in 1948 when it served as the university's primary source of power until it was decommissioned in 1975. After that, it served multiple purposes. However, today it is primarily used for storage. For the scope of this project, it is easiest to break it up into two separate goals. For Phase 1, we have the Shaw Power Plant renovation and expansion. In order to meet the MSU master plan, the plan is to renovate and expand the existing Shaw Power Plant into a 4-story academic building. This will house the science, technology, engineering, and mathematics classrooms and learning facilities. The building will require a stormwater plan and parking alterations to meet the new demand, as well as new signal timing for the surrounding intersections. For the second phase, we have alterations that must be made to Shaw Lane. The university will address the safety of pedestrian traffic by closing the north section of Shaw Lane and converting the south section to two-way traffic as opposed to one-way. This will result in new signal timing, bus accommodations, alterations to parking around the area, accommodations for bike racks, and coordination with the stormwater systems. So now we'll take a closer look at the job site and the surrounding area of the job site. So Phase 1 will mostly take place in this section here, where we have the existing Shaw Power Plant. That's where our changes we made to the building and the surrounding area for Phase 1. For Phase 2, this is Shaw Lane. It runs east and west. This is the north branch of Shaw Lane that will be converted to pedestrian traffic. And this is the south branch of Shaw Lane that will be converted to two-way traffic. And then these are some of the intersections that we will have to address with the transportation group.
Everyone, my name is Gabe Gaskin, and I'm the Geotechnical Engineer for Student Engineering Services. Today, I am going to discuss the overall foundation design for the brand new STEM facility on Michigan State's campus, as well as the procedures that led to this final presentation. To begin any geotechnical project, especially a rehabilitation one, with a current structure, you must first review the existing site conditions. This was done by taking a look at the 2018 geotechnical report provided by Materials Testing Consultants Incorporated, as well as their initial Shaw Lane Power Plant construction plans from 1946. The next step was to design a series of representative soil profiles portraying the existing site conditions, such as their soil type and strength parameters. Then came the task of designing the actual foundation system, capable of supporting the 4-story STEM facility and its lower basement level with retaining walls. Finally, an overall cost analysis was performed to show the economical impact of such a large project. Soil development began with the creation of distinct generalized cross-sections, one for each cardinal direction. These profiles are a combination of data from 3 to 4 of the 8 soil borings drilled by materials testing consultants in 2018. The locations of these borings can be found in the diagrams to the right of your screen. Each profile provides a detailed display of several key factors, including the stratified layers, elevations, and locations along the central baseline. While these certainly represented the nature of the soil beneath the surface, they were too complex for design purposes. Thus, each one underwent a simplification process, which combines similar soil types, SPT N values, and compressive strengths. Additionally, the individual layers were flattened based on average elevations to ease calculations down the road. It was noted that during this process, soil boring B6 displayed significantly weaker strength parameters than the recently created profiles, and therefore it could not be ignored, so a fifth cross-section was created. I have provided a few examples of these aforementioned profiles on this slide. To the left-hand side of the screen, you will find a generalized profile of the project's southern end. It combines borings B5, B7, and B8, showing off a multitude of various sand, clay, and silt layers. In the upper right-hand corner of the slide, the idealized version of the profile created in Microsoft Excel can be viewed. This cross-section was found to best represent the soil beneath the proposed northwestern structure and was selected for design based on its abundance of weak, silty sand and low plasticity clay. It also contains some of the lowest uncombined compressive strengths of any profile with low SBT-N values as well. In the lower right-hand corner of the slide is the idealized version of the B6 profile. This cross-section was found to best represent the soil beneath the proposed southern structure and was selected for design based on its extremely low-strength layer of gray, silty clay, noted from an elevation of 827.6 to 820.6 feet. This layer contained SPT-N values of just 3 and 4 blows per foot, making it a viable candidate for the final design. After consulting with Student Engineering Services structural engineer Matthew Chavetta, a rough schematic of the overall architectural layout was acquired. The AutoCAD drawing to the right of the screen details the two distinct sections of the proposed STEM facility, as well as their column spacing. Now, with the soil profile selected and the architectural layout determined, deliberation over which foundation system to design could commence, but not before considering an important aspect of the Michigan Building Code. Section 1804 states that excavation for any purpose shall not reduce the lateral support from any foundation or adjacent foundation without first underpinning or protecting the foundation against detrimental lateral or vertical movement. This was an extremely important factor when making the ultimate design decision for the STEM facility's foundation, due to its close proximity to the existing Shaw Lane power plant. With that being said, the first option for the foundation was spread footings. These would be the cheapest alternative. However, they could result in undercutting and large amounts of soil displacement. Plus, both immediate and consolidation settlement would also have to be considered. The second route was to opt for driven piles. While ideal for sites with poor soils at shallow depths, such as those found within the project limits, and the lack of settlement concern, driven piles are less cost-effective and result in both soil displacement and excess vibratory motion. After reviewing Section 26-81 of East Lansing's City Code, which states that a permit must first be obtained from the city manager in order to authorize the erection, excavation, demolition, alteration, or repair of any building, except between the hours of 7 a.m. and 8 p.m., these two were off the table. So, Student Engineering Services recommends the use of end-bearing auger cast piles instead. Also known as continuous flight auger piles, these are created by pouring concrete through the center of a hollow drilled shaft to a desired pile height and then lowering reinforcing steel into the hole before the cement has set. A visual breakdown of this process can be seen in the upper right-hand corner of this slide. The design utilized for the STEM facility consists of 18-inch diameter concrete piles strengthened with 8% reinforcing steel. These will run approximately 32 to 39 feet in length and will result in a pile socket at their tip in order to ensure a proper footing in the weathered shale bedrock beneath them. These piles will be arranged in groups of 4 with a 2x2 configuration and an internal spacing of 4 pile diameters, as shown in the bottom right-hand image. The following few slides pertain to the specific values calculated for the design of the STEM facility's foundation. As mentioned previously, the pile groups will have a 2x2 square configuration with a 6-foot spacing between pile centers and an overall width of 7.5 feet. Individually, however, each pile must meet the following specifications. First, a factor of safety against bearing capacity must be checked. With a factor of safety value of 3, the overall load applied to a single pile must be lower than the ultimate bearing capacity of the bedrock beneath it. Second, when it comes to the structural integrity of a single pile, the load applied must not exceed the allowable compressive strength of the concrete and steel columns. The designs proposed by Student Engineering Services meet these specifications, and a summary of the major calculation results can be viewed in both the spreadsheet to the left and in the table below. Before any of these aforementioned piles can be placed, however, a basement excavation must occur. In order to accommodate a 12-foot basement design, an excavation depth of 14 feet was required. Furthermore, an over-excavation for the site was necessary, as mandated by the Occupational Safety and Health Administration, since the excavation exceeded a depth of 5 feet. This over-excavation consists of a 2-foot horizontal section outside of the basement perimeter for workers to stand on while constructing the retaining walls, as well as a 1-on-1 sloped sidewall for climbing out in the case of an imminent collapse. A diagram of this over-excavation can be viewed in the bottom left. In total, 20,170 cubic yards of earth and material must be removed from the project site. Now on to the retaining wall design. In order to combat the lateral earth pressure and retain the soil behind the basement walls, reinforced structures must be utilized. For this particular project, a cantilever retaining wall was designed for both the southern and northwestern sections of the building. Each of these walls will consist of a 14-foot height with a base width of 7 feet. Additionally, each one is designed to remain in an at-rest condition, one with 0 horizontal strain. This is done by restricting motion at the top of the wall due to its connection to the building's structure, and by designing each structure with a factor of safety against sliding along its base. This factor of safety must exceed a value of 1.5. In addition to sliding, a factor of safety against bearing capacity must exceed a value of 3. The results of the hand calculations shown to the right can be found in the table below. The following are some hydrological concerns that Student Engineering Services had while designing the basement of the STEM facility. First off, the slab or basement floor rests just a mere 6 to 12 inches above the groundwater table. And secondly, the building's location is not far from the Red Cedar River and its 100-year floodplain, as shown in this map from IPF. With that being said, the following 2 alternatives were considered in the case of a high water event. The first option was to seal the basement watertight and combat the buoyant uplift by ensuring that the 62.4 pound per cubic foot uplift force does not exceed the building's self-load. The second and selected alternative is to utilize a sump pump system to remove water from the base of the foundation walls. If the pump fails during a high water event, however, the basement and everything in it is likely to flood. Now, while this is certainly not ideal, it is the safer of the 2 options, and it is the route that Student Engineering Services recommends. So with the finalized designs completed, cost is the remaining key factor when it comes to constructing the new STEM facility. An attached breakdown of numerous pay items relating to this rehabilitation project can be found to the right. Here are several codes listed for line items taken directly from the 2019 MDOT Weighted Average Item Price Report. For quantities estimated based on other external sources outlined in the notes column, item numbers are not provided. However, a summary of the assumptions can be found in this aforementioned column. In addition to high cost contributing items such as earth removal, reinforcing steel, and concrete, a 2.5% contractor staking fee, 10% contingency in the case of cost overruns, as well as the construction and preliminary engineering fee have been accounted for in the overall estimated cost of nearly $9.9 million. This concludes my presentation on the foundation design for Michigan State University's STEM Teaching, Learning, Interdisciplinary Research Facility. At this time, I would like to thank everyone for their attention and hand the microphone over to my colleague. Thank you very much. Greetings, everyone. My name
Hi, my name is Matt Shavetta. I'm the structural engineer for Student Engineering Services, and today I'll be going over the structural analysis for the new STEM Teaching, Learning, and Interdisciplinary Research Facility on Shaw Lane as part of the MSU 2020 Master Plan. After being hired by the client, Michigan State University, a scope was developed in order to organize tasks that needed to be completed for the successful delivery of this project, and this was broken up by the different divisions of Student Engineering Services. For the structural work, a layout had to be designed based on architectural, structural, geotechnical, and environmental considerations. There will be other aspects of this project, such as the redesign of pavement and traffic on Shaw Lane, but this will be handled by the respective divisions of Student Engineering Services. The structural frame of the building had to be constructed out of either steel or concrete, and steel was chosen as the material of choice based on the structural division's experience using the material and its ease of use during construction. And to comply with best practice, the building must be able to resist loads that it will see during its service life to make sure that it does not fail or collapse. And these loads were developed in accordance with ASCE 710 and AISC Manual 15th edition, and these are both accepted by the International Building Codes and State of Michigan Building Codes. The loads that the structure is going to be experienced throughout its service life must also be transferred to the foundation, which is designed by the geotechnical department. And working with green design, the building must have a sustainable design and also sustainable methods of construction and operational practices once it is in use. In keeping with a sustainable design for this project, it was decided that the decommissioned Shaw Lane power plant would be able to be refurbished and tied into the new STEM learning facility. 2 new buildings will be constructed adjacent to the Shaw Lane power plant, and it'll be tied in through a walkway. And the structural design of these 2 new buildings is what was tasked to Student Engineering Services. The refurbishment of the Shaw Lane power plant will be handled by a different engineering firm. Once the general location of the new STEM facility was agreed upon, it needed to be determined where specifically the 2 new buildings would tie into the Shaw Lane power plant, and this was aided by a geotechnical inspection of the surrounding area. Between the power plant and Red Cedar Road, there are existing utilities, so to avoid tearing up these utilities, it was decided that the building should be tied in on the west side of the power plant. And as seen in the diagram, part of the building will be constructed on an existing parking lot in the area. So this parking lot will need to be removed for the new building, although there is plenty of parking available in the vicinity for both teachers and students to use. And by constructing on a parking lot, it'll reduce the amount of green space that is torn up through the addition of this new building. There were several constraints that were required by the client for this project, and these constraints were that the academic building must be 4 stories, including a basement, and should be between 55 and 65 feet tall, including the roof. And the building is to be multi-use for both teaching and research purposes, and the breakout of the floors should be as such that the first floor would be administrative offices and computer labs, the second and third floor would be classrooms and communal workspaces, and the 4th floor would be faculty offices and research labs. And the reason for this is that the rooms with the highest turnover should be towards the bottom of the building, and the rooms with the least amount of turnover should be more towards the top. And there should also be an appropriate number of elevators, stairwells, bathrooms, and other such rooms according to code standards and best practice in civil engineering. And because the building is multi-use, it should have a collaborative environment throughout the building. This table shows a breakdown of the sizes and number of rooms that are required for the new STEM learning facility. And based on the final design of this building, all the room type numbers were either met or exceeded in the design. This slide shows a sample drawing of the architectural layout for the various floors. The walls are straight lines and the squares are the columns in the building. And this is the second floor. It shows the larger and smaller classrooms as well as locations for stairwells, bathrooms, and elevators. This is a sample drawing of the structural layout. This is for the southern building, which will be 50 feet longer than the northern building, and it is constructed as a braced frame, so all connections will be pinned, and it will not resist moments. These forces will be carried by the bracing members within the structure. Based on the general service of the building and the environment it is constructed in, each member will experience different loads or forces through the service life of the building, and these can be broken up into different categories, namely dead, live, roof live, snow, and wind loads. Earthquake loads are sometimes used in analysis, but based on the seismic activity and geography of this building, it was not required for this analysis. And these loads can be estimated by using ASCE 710 by knowing the occupancy and risk classification of the building. Once these are known, values for each of these loads can be found in the text and applied to the structure for analysis. And these loads will be factored and combined into different combinations through a process called load and factor resistance design. Essentially, the probability that a member will be able to survive a certain load is created into a probability density function. And the same is done with the loads that the member will experience and the probability it will experience those loads through its service life, as seen in the graph on the right. And the overlap of these two curves is the probability that the member will fail throughout its service life. There will always be some overlap between these curves because to create a member with infinite resistance would go against the cost effectiveness of this building. Once the structural design of the building was approved, SAP 2000 was chosen as the modeling program for this structure. And this program is useful because you can discretely analyze different structural members in the building in the elastic region, and most structures never want to experience forces that lead to it not being in the elastic region, so it serves its purpose. And through this program, you can select various materials and member shapes through a preloaded database, or you can design your own based on the materials and shapes that will be used in the final construction. And you can also assign different connections and boundary conditions between the members that represent what the structure will see throughout its service life. And then forces that were found through earlier analysis can be applied as various area loads, point loads, or linear distributed loads on members that will occur in field use. And then once the forces are applied, analysis can be run to see what forces and moments each individual member experiences, and these forces and moments will be graphed along the length of each member because they are not always constant along the length. And based on the sizes of the members and the materials used, SAP will also display if the member is passing, failing, or close to failing based on the forces and loads applied to the building, and if changes need to be made to make sure that the structure is stable. A 3D model of the building was constructed in SAP 2000. However, for analysis, only certain 2D frames that are representative of the structure need to be analyzed because the forces between similar representative frames are similar between the different members. So for this analysis, 4 total frames were chosen in the longitudinal direction, an interior and exterior frame, which is the long direction, and then in the transverse or shorter direction, also an interior and exterior frame was chosen. So in this diagram, this is the interior longitudinal frame. And for both buildings, a similar structural design was used, so only the analysis of the longer southern building was chosen. The northern building will experience similar or less forces throughout the structure. So by analyzing and making sure all the members pass in the southern structure, the northern structure will also be sufficiently stable as well. Once the structure was completely built in SAP and the forces applied on the structure, analysis could be run to determine the maximum forces in each member, and each member type was broken up into different categories: columns, beams, truss, and bracing members. And there are different forces that govern the failure of these members. So for columns, it is normally axial compression. For beams, it would be either bending moments or shear forces. And in truss and bracing members, it would be either axial tension or compression. So the maximum value that each member experiences was listed in tables such as these, and also the load combination that caused this max value was included in the table. And it was determined that designing a different member based on each maximum force would be not cost effective and would require too much design time. So the maximum force for each category, columns, beams, bracing members, and truss members, was found. And this value was used to govern the design of all columns, all beams, all trusses, and all bracing members throughout the structure. And the values were found to be similar for the northern and southern structure. This slide shows diagrams of the transverse direction. The one on the left is a representation of the interior transverse frame, and the one on the right is an exterior transverse frame, and this would be similar between both the northern and southern building. Once the maximum forces and moments were found in each member, they then could be used to size and shape each member. And the reason for this is that different geometries and cross-sectional areas resist moments in shear forces better, so this prevents the member from failing at all. And based on the classification of the member, be it a column, beam, truss, or bracing member, it's going to fail through different mechanisms. So for beams, they can fail through plastic yielding, which is when it bends and a plastic hinge forms and it eventually collapses, through shearing through a high enough force through the member, local buckling, which is when part of the flange or web will bend or crack in a localized region, lateral torsional buckling, which occurs when the beam bends and also twists, which is usually a governing case for longer beam members, and also deflection, because even if a member is not going to fail, you don't want it to feel like it is bending or unsafe in the structure based on the occupants in it. So the important characteristics for plastic yielding are to make sure that the beam has a high enough yield stress and moment of inertia. For shearing, it should also have a high enough yield stress and also a high cross-sectional area. For local buckling, this is based on the height and width of the flange and web sections of the beam. And for lateral torsional buckling, it is mainly based on the length of the beam. The longer the beam is, the higher probability that it is going to fail through lateral torsional buckling. And the deflection is based on the load applied uniformly across the length of the beam. And this value was determined from SAP 2000. Columns will fail through different mechanisms as opposed to beams, and the critical failure mechanisms in columns are crushing, elastic or inelastic buckling, local buckling, and flexural torsional buckling. To prevent crushing, the yield stress multiplied by the cross-sectional area should be higher than the force applied to the column, but this is not usually a governing state in steel. Usually the governing state will be elastic or inelastic buckling, which occurs when the column bows outward and has a bend. And once the column begins to buckle, it is no longer structurally stable, so there is a critical force that will cause buckling. And this force is based on the modulus of elasticity, the length of the member, the radius of gyration, and also the boundary condition of how the column is connected to either the surface or other members. And this can be used along with the yield stress to determine the critical value of stress for buckling. And this critical stress times the cross-sectional area should be higher than the force that is applied to each member. Local buckling in columns is similar to that of beams. It is a measure of if the height and width of both the flange and web are strong enough to resist local buckling. And then because the section shape is going to be a W-shaped section or an I-beam for columns as it is with the beams, flexural torsional buckling will not be a factor because this only occurs in sections that are not doubly symmetric. Bracing and truss members must be checked for axial compression and tension because they will experience both through their service life. For axial compression, they should be checked for the same failure mechanisms as columns, so crushing, buckling, local buckling, and flexural torsional buckling. And because WT sections, which are T-shaped sections, will be used for these members, flexural torsional buckling could be a governing factor because these members are not doubly symmetric, so this needs to be checked as a failure criteria as well. Once the members are sized for compression failure, they need to make sure they will not fail in tension, but because the members had similar maximum tensile and axial forces, tension will most likely not be a governing state, which it wasn't for this analysis. Some of the ways that tension members can fail are through gross yielding, which occurs when the entire cross-sectional area begins to yield, net fracture, which is when the member starts to break and fracture around the bolted connections, and block shear, which is another method in which the member begins to rip and tear away at the connections. And the members also had to be checked for slenderness ratio. Because of the large variance between the maximum axial force or bending moment between the different floors of the building, it was decided that 2 column and 2 beam shapes should be created, one that a column could survive up to 11,000 kips and one up to 300 kips, and then for beams, one that could survive a bending moment up to 450 kips, and then one up to 260 kips. And for bracing and truss members, because the variance in the forces was much closer together. It was decided that only one bracing and one truss member was needed for this design, and these member shapes are listed in the table. With the shape of each member known, the cross-sectional area could be determined and multiplied by the length of each member to come up with the total volume of steel used in the structure. This volume could be multiplied by the unit cost of steel, and when factored with the fabrication, erection, and connection cost, created the total cost of steel. The cross-sectional area of each floor was multiplied by an estimated thickness of concrete to come up with the total volume of concrete, which was then multiplied by the unit cost of concrete. The amount of rebar used on the structure was determined to be about 1% the weight of concrete. So with this value determined, it could then also be multiplied by the unit weight cost of rebar. Design fees were calculated as $40 per hour, and an hour log was kept for the design process, and engineering fees were determined to be about 2% of the cost of materials and design fees, which led to a total cost of $8.7 million for the design and erection of the structure.
Greetings, everyone. My name is Caitlin Commissaris, and I am the hydrology engineer for Student Engineering Services. I will be discussing the stormwater management system for this project today. The scope of work for the stormwater management system is as follows. First, a storm sewer system design will need to be constructed to handle a 10-year design storm with a time of concentration of 15 minutes. Drainage will need to be provided for the newly designed roadway as well as from the project site where the proposed building will be located. Low impact designs must also be incorporated into this system. And the retention pond design must be able to handle a 100-year, 24-hour design storm times 2 as specified by the Ingham County Drain Commission. These design objectives play a major role in the decision-making for this project. For example, low-impact designs must be aesthetically pleasing and fit into the general landscaping of MSU's campus. They also must be methodically placed so that they are directly incorporated and integrated into the stormwater management system and storm sewer design. And the proposed retention pond is to prevent frequent flooding for these design storm events as well, and further prevents deterioration of the Red Cedar River water quality because there is no outlet to this retention pond. And this design is also cost-effective and capable of being permitted from a regulatory standpoint by the Ingham County Drain Commission. The placement of each low-impact design was methodically thought out based on aesthetics as well as efficiency of the low-impact design in each proposed location. As you can see, the proposed new branches of the building are shown in blue, and there is a green roof proposed for the roof. Green roofs are another variation of a bioretention cell that have a soil layer laying atop a special drainage mat, material that covers excess percolated rainfall off the roof. This design would be used to facilitate drainage from the roof and may be coupled with various rain barrels. Rain barrels are shown in light blue on the sides of the building, and they are placed to collect runoff from the roof. The easternmost barrel will collect rain from the existing building as well as the proposed section of building to the west. And the second barrel is placed along the northern edge of the proposed building branch to the south. The placement of these barrels was thought out so that they're not easily visible to pedestrians that are walking along Shaw Lane or Red Cedar Road. And then shown in green are the vegetative swales, and they were placed here to provide extended time for water runoff from the roadway to infiltrate into the soil before collection in the retention pond. Vegetative swales are channels or depressed areas with sloping sides covered with grass and other vegetation. They slow down the conveyance of collected runoff and allow it more time to infiltrate the native soil beneath it. This water is then routed into the retention basin, and these swales will include vegetation that is native to the site location and that will provide a more aesthetic look that will fit into the campus surrounding scenery. Another low-impact design feature considered in this conceptual design is a bioretention cell, and that is shown in magenta. Bioretention cells are depressions that contain vegetation grown in an engineered soil mixture placed above a gravel drainage bed. They provide storage, infiltration, and evaporation of both direct rainfall and runoff captured from surrounding areas. And then another low-impact design that may be considered if desirable would be to implant permeable pavement in the Spartan Stadium parking lot. This would increase the cost of the project since drainage would need to be reevaluated for the parking lot and included in the storm sewer system described in this report. Once the low-impact design considerations were made, a model of the proposed storm sewer network was put together using EPA SWIM. This figure displays the division of the land into subcatchments. Shaw Lane was divided into subcatchments 1 through 6, and the site location was divided into subcatchments 7, 8, and 9. The inlets are located where runoff would flow based on existing elevation of the site and road grades. The elevation generally decreases towards the Red Cedar River to the north, and therefore most of the inlets are located to the north of each subcatchment. Runoff water is going to be directed through the storm sewer system and into the retention pond through 3 separate routes, and that's going to be shown on the next slide. As mentioned previously, water is routed into the retention pond through 3 different routes. As seen in this figure, the blue arrows depict runoff from each subcatchment into their respective inlet. We're going to focus on the yellow flow path first. As you can see, runoff from subcatchment 1 is directed into the first vegetative swale. Any water that is not infiltrated or evaporated during the process goes to outlet 5, which is then combining water with subcatchment 2 and entered into the second vegetative swale. And again, any water not evaporated or infiltrated here will then be directed into the retention basin. The green flow path shows site drainage from subcatchment 7, 8, and 9. As you can see, subcatchment 7 drains into junction 1, and then water is collected from subcatchment 8 and J2, and then it is directed into junction 4, which collects the water from subcatchment 9 and then into the retention basin again. And then finally we have the red flow path, which collects water from subcatchments 3, 4, 5, and 6. And this all is directed into the bioretention cell. Any water not infiltrated or evaporated here then goes into the retention basin. Each of these 3 flow paths and their subcatchments in each one have their own low-impact designs incorporated. The yellow flow path has the vegetative swales incorporated into it, and then the red path has the bioretention cells. And the site development, of course, has the green roof and the vegetative swales. Calculations made for the storm sewer system design were done using the following methodology. The design storm is going to be a 10-year design storm with a time of concentration of 15 minutes, and the rainfall intensity was determined by the MDOT Drainage Manual Rainfall Intensity Duration Table. The flow may be calculated in each pipe using the rational method, which is Qmax equals C times I times A, where Qmax is in cubic feet per second, C is just a coefficient. and I is that rainfall intensity in inches per hour, and then A is the total area in acres drained by each pipe. The pipe diameter may then be calculated using the Manning's equation shown in equation 2. And then once we know the diameter and the flow in each pipe, we can calculate the velocity in each pipe, which must be between 3 and 10 feet per second as required by the Ingham County Drain Commission. And storm sewer invert elevations are calculated using the linear equation y equals mx plus b. The table shown on this slide provides the area in square feet for each subcatchment. These areas were found by measuring distances on Google Maps. Since most of my subcatchments are rectangles and squares, I was able to just multiply the length times the width to find the area in square feet, and then I converted this area into acres. And the T inlet, as mentioned earlier, is going to be 15 minutes for each subcatchment, and the rainfall intensity is 3.54 inches per hour. The table on this slide shows calculations using the rational method and the Manning's equation to determine the flow in each pipe in cubic feet per second, as well as the diameter of each pipe in inches. There was some interpolation that needed to be done due to insufficient velocity in the pipes. As mentioned earlier, the velocity does need to be between 3 and 10 feet per second to meet the standards and requirements of the Ingham County Drain Commission. At first, the road was divided into various subcatchments, assuming the crown was in the middle of the road. However, the velocity in the pipes collecting runoff from these subcatchments was under 3 feet per second. The slope could not be realistically adjusted to fix that issue. Therefore, the subcatchment areas on the roadway needed to be increased. I had to coordinate with pavements to make it possible to adjust the crown of the road to be on the south side of Shaw Lane. Therefore, all the runoff is directed towards drainage structures on the northern edge of the roadway, as you could see in the stormwater system figure. And with this adjustment, the subcatchments were able to be expanded to the entire section of roadway instead of down the middle where the crown would have been. And this change really did fix the issue and made the resulting velocity in each pipe within the required range. So this table here shows the storm sewer invert elevations. Each inlet and outlet, I went into the AutoCAD basemap campus file and found the ground elevations at each junction or outlet. And then, according to the Ingham County Drain Commissioner's manual, each pipe has to be at least 3 feet depth underground. So you can see here the depth underground is at least 3 feet or more at every location. The invert elevations were calculated based off of the linear function y equals mx plus b, as mentioned earlier, where x is the slope of the pipe and m is the distance, and then b is the initial elevation, or the ground elevation minus 3 for the starting point for each of the 3 flow paths, as mentioned earlier. And as you can see, outlets 1, 8, and 7 all around the retention pond over here are all at the same depth. And that is because we want the outlets to all be at relatively the same depth. We don't want them to be scattered at different depths in the retention pond. And as you'll see later, the retention pond was calculated to be 5 feet deep, and this depth underground is 6 foot deep. So there'll just have to be some grading done of the retention pond to ensure that the pond's about 5 foot deep and has gradually sloping sides as well. Here is the profile view of the bioretention cell. As you can see, there are multiple layers to the bioretention cell. The top soil, we have a mulch layer, and then we have the bioretention soil, then we have the gravel bed. As you can see, the outlet is located within the bioretention soil. There will also be an overflow pipe as well that will come out of the top of this. And here is a profile view of the vegetative swales. The top elevation is the ground elevation, and as you can see, the outlets are all here from what we calculated previously for the inverts. And as you can see, the bottom slope of the vegetative swales matches very closely with the sewer pipe that lies within it. The methodology for designing a retention pond is as follows. First, we need to calculate the required storage volume for a 100-year, 24-hour design storm event, and the retention pond must be able to store double this volume as specified by the Ingham County Drain Commission. To calculate the volume of storage needed, we can multiply the rainfall intensity by the total areas drained in acres, by the average runoff coefficient by 2, and equation 6 shows how to calculate that runoff coefficient. And then we can calculate the surface area of the pond by dividing the volume by the desired depth. And then to calculate the dimensions of the pond, we can solve for the area of an ellipse since the pond is going to be in the shape of an ellipse. The equations listed on the previous slide may now be used to determine the dimensions of the retention pond. First, the volume is calculated in acre-feet by multiplying the rainfall intensity, which is 5.85 inches found from the MDOT tables for a 24-hour 100-year storm, multiplied by the total area, which is 7.435 acres, times the average runoff coefficient, which is 0.645, and then multiplied by 2. And then the desired depth of this retention pond is going to be 5.5 feet, so we can divide the volume by that to get the surface area in acres. And then we can solve for the dimensions A and B, and that gives us 150 by a 75-foot ellipse. Here is the plan view of the retention pond with the dimensions calculated from the previous slide. As mentioned, A is 150 feet and B is 75 feet. The top elevation of the pond is going to be 847 feet, and it'll be 5.5 foot deep. For safety reasons, the sides of the pond will be gradually sloped, and it will be the deepest point in the middle of the pond. This design meets all the previously mentioned objectives. The low-impact designs chosen are directly incorporated into the stormwater management system, and they are placed methodically so that they are both aesthetically pleasing to MSU's campus and they fit into the general landscaping. And the retention pond retains all runoff from the site, therefore preventing any deterioration of the Red Cedar River's water quality. And the storm sewer system and retention pond are designed for their required storm events to prevent flooding as required by the Ingham County Drain Commission. Cost analysis will also be provided by the project manager.
Hi, my name is Jason Andable. I'm the transportation engineer for Student Engineering Services, and this is the Shaw Lane Road Diet and Reconstruction. So to start, a road diet is a reduction in the number of lanes in a road usually. This is done to simplify the design and typically to make it easier on pedestrians and bicyclists. This road diet will go from Farm Lane, right here, to Red Cedar Road on North Shaw Lane, so this stretch right here. This area is the heart of campus, I would say. The International Center and Wells are two of the most popular buildings, and then tons of people have classes in engineering at Anthony Hall. Additionally, the new Shaw Lane Power Plant building, the STEM building, will see a lot of traffic too. And parking lots 39, 40, and 38 almost always are filled. The traffic from North Shaw Lane will be moved to South Shaw Lane, and this will require an increase in the number of lanes on South Shaw Lane and signal retiming and other geometric adjustments. So the first step in this process was data collection. It's important for any engineering design, especially roads, to be designed for the future. Since MSU is kind of enclosed on its own, we didn't feel that a standard growth rate would reflect campus that well. So we used enrollment data going back to 1992 up to current to predict the future. We used a linear fit and found the growth rate to be about 0.7% per year. In order to be conservative, we doubled this to 1.5%. The next step in this process was to apply the growth rate and redistribute the traffic. So the existing maximum values for each approach were tabulated in Excel. Then a standard exponential growth function was used using the present volume, the growth rate, and the number of years. Traffic from westbound North Shaw Lane was redistributed to South Shaw Lane. And then traffic volumes throughout the rest of this intersection needed to be adjusted in order to account for these changes. The third step in this process was the synchro design. The updated traffic volumes calculated previously were added into Synchro, which is a traffic modeling software. The lane distributions and basic geometry were adjusted in order to make sure that this could handle the traffic volumes calculated. Additionally, the signal timing and phasing had to be adjusted in order to provide the best level of service possible. The intersection as a whole was rated a B, with several of the best approaches being A and the worst being a C. Here you can see the signal phasing and timing for each approach, going from eastbound left, eastbound through right, westbound left, westbound through and right, and so on. Left turns used the leading left formation, which were protected, as well as permitted left turns during through traffic. The protected phases are shown for each signal, as well as the permitted phase. The split for green time, yellow time, and all red is shown, as well as the level of service, ranging from A to C, with C being the lowest and B being average. The next step in this process was the geometric design, which was done in AutoCAD. The lane configuration found in Synchro was used as a baseline. As previously stated, North Shaw Lane was turned into a pedestrian bike trail. This required the associated parking lot to its entered or exit from or to North Shaw Lane to be relocated. Since South Shaw Lane had to be widened, the sidewalk in front of Engineering Building and Anthony Hall were moved closer to the buildings and away from the road. 11-foot lane widths were used with 6-foot bike lanes on both sides and a horizontal grade of 2%. 2 full lanes plus a left turn lane were added to South Shaw Lane in order to handle the westbound traffic, and this also required the parking lots to be reduced in size slightly. A right turn lane was added to northbound Red Cedar Road, and the lane distribution on Red Cedar Road had to be modified to fit the new geometry. Here you can see the geometric design. As you can see, North Shaw Lane was integrated into the existing sidewalks and pedestrian infrastructure. This is to make transversal easy for pedestrians. South Shaw Lane was expanded 2 more lanes to account for westbound traffic, and the sidewalk was pushed back. There was several changes at the intersection. A right turn lane was added on North Red Cedar Road. A widened right turn going southbound was also added, and the lane distributions were changed to account for the lack of the signal that was formerly here. So to continue, there were several special design features present within the design. The first of these I already touched on, which was this right turn lane added onto southbound Red Cedar Road at South Shaw Lane. This was added to avoid this acute angle, which cars may have been able to transverse, but it would have been problematic for buses with their increased turning radius to handle this. Additionally, a bus bay was added in front of Anthony Hall. This was so that buses could stop and pick up students without having to impede one of the lanes of traffic. Also, more bike lanes were added in front of Wells and International Center on the former North Shaw Lane. The next step in this process was cost analysis. For transportation, the cost calculated included sidewalk addition removal, curb addition removal, lane striping, and signal addition removal. Other costs within the project, such as construction, paving, and drainage, were calculated by my teammates. The total cost for transportation came out to $262,404. Our current recommendation includes having only 1 bus bay on the south side of South Shaw Lane instead of 1 on each side. This was done as we feel that more pedestrians would gather on this side and we didn't need to further cut back the size of parking lot 40. We chose 11-foot lane widths to strike a balance between a safe size and not taking up too much space. We recommend that MSU integrates more bike lanes in the South Shaw Lane outside of the scope that would tie into the ones that were inside of the scope. Our main current limitation includes not having farm lane signal timing. As such, the need for a pedestrian signal couldn't be determined because we didn't have the gaps coming from that side. This concludes the transportation portion for student engineering services. Thank you.
Hi, my name's Emily Estrada. I did the pavement design for the Student Engineering Services group for our senior design in civil engineering. This slide outlines the scope of the pavement engineer on the project. So our data collection phase involved a soil investigation, mainly pulling from the 2018 geotechnical investigation of the site, a condition survey where one of our team members went to West Shaw and took some pictures of the existing conditions of the road, and then regulations. So I looked really heavily into the 2004 MSU IPF specifications that pull from a lot of different regulations that we needed to use on campus. The preliminary analysis goes over some changes to the road geometry that we're proposing and our drainage plan. And then finally, we will give the cost analysis for the detailed analysis and some recommendations based on what we found throughout our research. Jumping into the soil investigation, we got our borehole data from the 2018 geotechnical investigation of the site, which referenced the 1994 geotechnical investigation of the site. I read both, and the in-depth analysis was done by our geotechnical engineer, Gabe Gaskin. He produced some soil profiles for us, which I then used to estimate my modulus of resilience. So the soil that I was interested in was mainly SM or SP-SC for the SES classification, which told me to use a 20,000 PSI for my modulus of resilience estimation. And then additional parameters I found in the report were where the water table is, depending on the conditions of the red cedar, and the general moisture content of the soil. This shows a few important snippets of the borehole data. So there were several profiles drawn using information from all of the holes, but this was the one that I found most important because it's bordering where a lot of closest to where the pavement would go. And then the upper depth was really all that we were concerned about, which is clearly SM or SPSC. Moving into our condition survey, which focused on West Shaw Lane, we had someone on the team go out and take some pictures so that we could analyze them. This one was taken about 6 feet east of Chestnut Road, and most of West Shaw looked this way. Not severely distressed, about a 2.5 service rating, just by my personal experiences driving on it. It's overall acceptable to drive on, but there is some room for improvement. You see these long cracks that are parallel and perpendicular to the curb that are telling us it's more of oxidation of the surface layer of asphalt over time or some freeze-thaw distress, but we don't see a lot of evidence of foundational distress, which is telling us that really only a mill and fill might be needed. These were the two special cases that were found in our survey of West Shaw. So the top figure shows some alligator cracking that was found in some zones of the road that was mainly concentrated towards the curb and gutter, which I thought was interesting because that could be the water that is collected there due to the grade is sitting there and it's freezing and thawing and it's distressing the pavement more heavily in those areas, or it could be evidence of something going on in the pavement structure foundationally that we're going to need to reconstruct. And then the bottom figure also shows the most significant area of distress on the stretch of the road, which was near the crosswalk. And this could be due to the extra loading of people walking on the crosswalk or cars sitting there and waiting. Either way, there's clearly some significant distress going on, and we would like to learn a little bit more about this area to see if there's a foundational reconstruction need. This was the cross-section that was found for the parking lots. This is actually made available to the public by MSU. You can find it with a Google search. We decided to mill off 2 inches in all of the lots within the scope. This is the cross-section for the roads. All the roads in the scope, we planned for a 3-inch mill and fill because the distress was a little bit more severe on the roads than it was in the lots. This is also labeled Figure 2 because it's referenced in some of my drawings in the next few slides. It was Figure 2 in my personal report. Lastly, for cross-sections, I included the standard sidewalk that they use on campus. There is going to be some sidewalk removal associated with the expansion of South Shaw Lane, but that cost analysis is included in the transportation engineer's scope. I just thought it would be helpful to include this cross-section since we are working with sidewalks a little bit. Moving into the road geometry changes, so the majority of the paved area that we are working with in the scope is staying the same. We just wanted to highlight a few areas where it's changing. The big one is definitely South Shaw Lane because we're expanding a little bit to the north and a little bit to the south. There's going to be reduced areas for lots 39 and 40, and we're encroaching on a little bit of that sidewalk that's going to be removed south of Shaw Lane. And then in the figure, the existing road is shown by the magenta, and then the proposed is the cyan. Next, we have geometry changes for Red Cedar Road. So this island here is going to be changing shape. Red Cedar needed to change shape to accommodate for some traffic changes. And then we're actually only paving this stretch of North Shaw Lane so that it can change shape from this magenta to this cyan and now accommodate just pedestrian and bike traffic. Lastly, we've got changes to Lot 79E. So Lot 79, the majority of that lot will remain exactly the same, but this part of it was being taken over by the proposed building, so we had to chop off that little piece of it, and we wanted to keep the rest of it so that there is additional faculty parking or anything else that we might need to use that little space for. Moving into our drainage plan, I was mostly responsible for assigning a grade to each stretch of road that we were repaving and then picking a crown point. So the hydrology engineer let me know that we needed the majority of West Shaw Lane to be draining north. So I put the crown point at the southernmost lane edge. My PE let me know that it's standard to keep the crown point at a lane edge even if it's not in the center. So we decided to put it right here, and this will actually be a continuous point from here through the expanded South Shaw Lane. You can see here in the South Shaw Lane profile that shows all the lanes that are to exist for our proposed plan, and then the crown point is at this lane edge shown right here, which would be continuous from where we put it in West Shaw. There are two profiles drawn up for Red Cedar Road. So this one shows Red Cedar north of Shaw, which all has the same amount of lanes, and the crown point is in the middle. The amount of lanes on Red Cedar increases when you go south of Shaw Lane, so that's why our profile is bigger here and needs this match line to show the whole thing. But it is a continuous crown point from Red Cedar north of Shaw and then Red Cedar south. Lastly, we have our profile for that small section of North Shaw that we're paving. You can see right in the middle and in the previous slides, figure 2 is pointed out, which is just saying that this is where the road cross-section would go that we showed in the previous slide. I also included the hydrology map here, so you can see this stretch of West Shaw where we have S1, S2, and S3. That's where we needed the road to all be draining towards the north of campus. So the crown point was put as south as possible. Moving into our detailed analysis, which outlines the cost of all these options that we talked about. So there are several different approaches that could be taken, like crack sealing or milling a different depth of the pavement. This is just what we chose to consider for our budget. So 3 inches of milling and filling on all of the roads, and then 2 inches of milling and filling on all of the lots. And then the only other significant cost that would have been considered would be the expansion of South Shaw Lane by 1 lane. This is just the results of the cost analysis. So the total cost of the paving that we're proposing is about $1 million.
Hello everyone, my name is Avery Dykman and I am the environmental engineer for the Student Engineering Services team. Today I will be discussing the design of a treatment system for the removal of PFAS from contaminated water at a chosen site in Michigan. The objective of my project was to design a GAC column appropriate for the conditions at the site to remove PFAS from the contaminated water. The system needs to be able to effectively remove PFAS to below regulatory guidelines set by the U.S. EPA and the Michigan Department of Environment, Great Lakes, and Energy. The design focuses on the removal of PFOA and PFOS because these are 2 of the most widely used PFAS in the world, and their removal is slightly easier because they are longer chain PFAS. And the design also needs to be cost effective. So for a quick overview of PFAS, they are a group of over 4,000 man-made chemicals, and their production and use began in the 1940s. They have a wide variety of uses in consumer goods, including apparel, leather, plastics, cookware sealants. It's found in a lot of food packaging and in aqueous film-forming foams that are used commonly for firefighting practices. Their chemical properties make them very difficult to manage. They have a strong carbon fluoride bond that prevents them from breaking down naturally in the environment, meaning a treatment technology must be implemented to clean up contamination resulting from these pollutants. And exposure to these compounds has been proven to cause many health effects in humans, including liver and kidney cancers, pregnancy complications, thyroid disease, and high cholesterol levels. So due to the widespread use of these compounds and the increasing concern over the harmfulness they have on human health and the environment, it was necessary for the federal government to step in and place some type of regulation on the amount of contamination that is safe to be present in our environment. These compounds were not regulated for a very long time, and they were just able to accumulate in the environment over the years that they were being used, until finally in May 2016, the United States EPA officially recognized them as a hazardous contaminant, and they established a health advisory exposure limit for PFOA and PFOS at 70 parts per trillion combined concentration. And then the state of Michigan took it even a step further and lowered the drinking water criteria in 2020 to 8 parts per trillion for PFOA and 16 parts per trillion for PFOS. Michigan is actually one of the leading states in PFAS monitoring and has taken the most steps to try to control contamination in our region. Eagle launched a industrial pretreatment program for PFAS to help wastewater treatment plants around the state that are struggling with this type of contamination get grants and help them implement their own treatment systems to try to control the issue. Many studies have previously been completed that prove conventional treatment methods such as coagulation, oxidization, UV radiation, disinfection are not adequate for the removal of PFAS due to their complicated chemical makeup. Instead, advanced treatment technologies must be implemented, and some of these include ion exchange, reverse osmosis, and GAC adsorption. GAC adsorption will be the treatment technology utilized to control PFAS contamination at the selected site in Michigan. GAC stands for granular activated carbon, and GAC adsorption works by sending the contaminated fluid into a GAC column containing a bed of the activated carbon. When the wastewater flows through the column, the contaminants can come in contact with this activated carbon and adsorb to the surface, thereby removing them from the wastewater stream. Once the carbon becomes saturated, it must be changed out or reactivated because it will no longer be effective in removing the contaminants from the wastewater. And longer chain PFAS have greater absorptive capacity, meaning it is much easier to remove them than shorter chain PFAS compounds. And the diagram on the slide shows a simplified version of this process. There are many factors that influence the performance of a GAC column. The bed dimensions are very important. It should be sized appropriately to meet the demands of the flow rate and initial PFAS concentrations present at the site where the column is being used. The carbon absorption capacity is also very important. If the carbon is unable to absorb the target contaminants, it will not be effective in treating the wastewater. pH and temperature also play a role in the effectiveness of removal. In order to select a site that would benefit from the implementation of a PFAS treatment system, data provided by Eagle was used. They have done extensive monitoring all over the state to identify locations struggling with this type of contamination. And the location that I chose was the Muskegon Wastewater Management System and Metro Wastewater Treatment Plant. This site has consistently violated the regulations set at the federal and state level. The average PFAS concentration found at this site was around 28 parts per trillion, and the average flow rate entering this plant every day is 42 million gallons, which is a very large volume of water. Eagle was also able to identify several industrial sources in the area that contribute to the PFAS contamination entering this wastewater treatment plant. And since the volume of water treated at this plant is so large every single day, it will be much more cost effective and simpler to install a treatment system directly at one of the industrial sources for the pollution in the area. The industrial source that I thought was most appropriate for the implementation of a treatment system was the Muskegon County Airport. This site frequently uses aqueous film-forming foams for firefighter training activities that are required by the Federal Aviation Department. The average concentration of PFAS leaving this location is around 79.6 parts per trillion, which is well over regulations set at the state level. Eagle has done extensive monitoring at this site at 9 different monitoring wells. There is currently no data available on the amount of groundwater leaving the site per day, so an assumed value of 100,000 gallons per day was made. And Eagle was able to provide the information that groundwater flows to the northwest corner, so the treatment system will be placed there since that is where the groundwater is already naturally flowing. When designing a GAC column, there are several different models that can be applied to evaluate the performance of the carbon in removing the targeted contaminant, and these include the Bohr-Adams model, the Thomas equation, the scale-up approach, the empty bed contact method, and the mass balance relationship. During the process of writing my literature review, I thoroughly examined all of these methods and learned how to apply them, and I decided to use the Bohr-Adams model for my design because it allows for flexibility and is relatively simple in application. The equation shown on the slide represents the Bohr-Adams model, where CO is the initial concentration, CE is the effluent concentration, K and NO are experimentally determined parameters, so these will be established based off of previous studies that have been completed. D is the bed depth, VL is the approaching velocity, and TB is the breakthrough time. In order to apply the model, we must have first established some of the design criteria and parameters. So 4 GAC columns will be used at the site operating in parallel in order to meet the demands of the flow rate and concentrations present at the site. The initial concentration is 79.6 parts per trillion or nanograms per liter. The effluent concentration should be 16 nanograms per liter, which will meet these regulations set by the state of Michigan. The flow rate at the site is 100,000 gallons per day or 25,000 gallons entering each column. The approaching velocity, which can be calculated by dividing the flow rate by the area of the column, was 32.2 meters per minute. A GAC bed depth of 6 meters will be used, and the columns will have a diameter of 3 meters. Since the columns are operating in parallel and have the exact same dimensions, it can be assumed that their performance results will be the same. And so the Bohr-Adams model can be applied to calculate the breakthrough time by rearranging the equation shown on the previous slide. The parameters used for this design yield a breakthrough time of 50.5 days. In other words, the carbon cycle will last for 50.5 days before it needs to be reactivated or changed out. This yields 7.23 carbon cycles per year. We want this number to be as low as possible so that there is not a large number of maintenance required and someone doesn't constantly have to go in and reactivate the carbon many times per year. This slide is just showing a continuation of some of the equations used in the Bohr-Adams model. The PFAS removed per cycle was able to be calculated at 151.6 grams per cycle, and the absorptive efficiency was 98.3%, which is very good and acceptable for a design system. The table shown here is a summary of all of the design parameters that were determined for the GAC treatment design at the Muskegon County Airport location. It indicates the flow rate, the PFAS concentrations leaving and entering, the number of columns that will be needed, as well as their dimensions, the breakthrough time, the amount of carbon needed per year, the amount of carbon cycles per year, as well as the overall effectiveness in removal of PFAS from the wastewater at the site. These parameters could be applied to the implementation of a full-scale treatment system at this location. This diagram illustrates the GAC system that will be implemented at the site with the correct dimensions and flow rates, as well as PFAS concentrations leaving and entering. This is a simplified diagram, but this is roughly what the treatment system would look like when applied in real life. When designing a GAC treatment system, it is also very important to select a carbon that is best suited to remove the pollutant that you are targeting. Hydrodarco 4000 has been proven to be a superior absorber of PFOA and PFOS. This is a lignite-based activated carbon. It has high porosity and large quantity of absorption sites for the PFAS to adsorb to. Because of its superior performance, it leads to lower operating costs because less frequent carbon changeouts will be needed, resulting in a lower volume of carbon needed per year. The diagram on the bottom shows the breakthrough curves comparing this carbon to other carbons. Hydrodarco 4000 is represented by the blue line, and as shown, it is able to treat a much higher quantity of bed volumes of water before breakthrough is reached. So in conclusion, the design of the GAC system achieved is able to effectively remove PFAS in order to meet federal and state regulations at the location. This was the most cost-effective design approach by applying the treatment directly to the industrial source rather than attempting to treat the large volume of water that enters the Muskegon wastewater treatment plant every single day. By treating water at this source, it will significantly decrease the PFAS concentrations found at the wastewater treatment plant because this is such a significant contributor to pollution in the area. I hope you enjoyed my presentation, and thank you for listening.
So now that we've gone through all of the project designs, we're going to go over the overall project cost. So each group member did their own cost analysis for their portion of the project, and they submitted those values to me, and I put together this table. So up here in the general category section, you have those values that were calculated by the team members, and then the subtotal based on those calculations is $37,687,192. And then below we have a lump sum category section. So these are just general costs to the overall project. And then these are based off of percentages, as you can see here, and the running subtotal to that line or that category. So then the subtotal down here you can see is $7,697,459 and some change. To the right you can see the total project cost, or total percentage of project cost, and then that total with the two subtotals combined. And then we calculated the grand total based off of a 15% contingency, and our final total is $52,192,349.50. So this will be the first of two construction schedules. This construction schedule represents the first portion of the project, which is the Shaw Power Plant construction and renovations. The start date for this project is May 10th, 2021, and we'll start off with acquiring the proper permits and all the stuff we need in order to begin the groundwork on the project. Once the permits are acquired, we will begin the site clearing, removing trees, parking lots, sidewalks, all that stuff to get the site ready. And then that will be followed up by excavation. And then after that, we have the foundation work and putting in the pilings. And that will be followed up by framing the building. That will be when the building kind of comes to life and we get the beams and columns in place, and then we'll have the roof construction and the exterior walls constructed, and then our plan is to have that completed by the middle of November, having that done before the real winter season begins will allow us to do all the interior work throughout the winter months, and we'll make it so we don't have to take a long break throughout those winter months. That will allow us to do the plumbing, electrical, HVAC systems, drywall, flooring, all that good stuff throughout the winter. And then in the following spring, we will be finishing up the building, meeting grades with the surrounding area of the building, and excavating the retention pond, and replacing sidewalks and vegetation and trees. And then the end date for the first portion of this project is May 16th, 2022. So that's when we had planned to have the first phase completed. Here's the second part of the construction schedule. This construction schedule just has the Shaw Lane alterations work on it. And this timeline is based off of the fact that we're going to do like a full closure. The full closure allows us to get it done a lot faster because we can do everything at one time. We don't have to close down half of the road, do it, close down the other half of the road and do it. So this setup will allow us to complete it in one summer or one road construction season, and to be done before school starts in the fall and after school ends in the spring. So we have the start date being May 23rd, 2022, and then the end date being August 25th, 2022. So as you can see, we start off with mobilization, work into traffic control, and then the actual road work begins on June 13th, where we demo the existing pavement. That's followed up by the new subbase and leveling and compaction, and then that will be completed on the 18th, and then we'll pour curbs and tie into the storm system following that, and then we will have new asphalt on the roadway and in the parking areas, and then we'll just have to finish that up by painting new lines and planting vegetation, and then that's how we get to our end date of August 25th. This concludes the design from Student Engineering Services for the Shaw Power Plant and Shaw Lane alterations. Thank you for watching.